Everyone can hear me, right?
Yes.
So yeah. Hi everyone, I'm Jishnu. I'm a second year grad student from Prashant Kamat lab. So today I'll be talking on light-induced expulsion of gold nanoparticles from the CsPbBr3 bromide gold nanocrystals. So since I have been given 10 minutes to present, I will start with the motivation and introduction behind the project. So we all know that semiconductor nanoparticles have been considered as a building block of light harvesting system, and their role in capturing incident photons to induce separation of charges in quantum dot solar cells and photocatalyst system is of particular interest. So among them, the perovskite nanocrystals such as CsPbBr3 bromide have been the focus of attention in the semiconductor nanomaterial field. So efficient transfer of charges across the semiconductor interface is the key for converting light energy into electricity or fuels. So one of the ways to increase the photocatalytic efficiency is to couple the semiconductor nanoparticles to noble metal co-catalysts like gold. So the noble metal co-catalyst like gold, it enhances the quantum yield of the photo-induced electron transfer processes by improving the charge separation within the semiconductor nanoparticle, also discharging the photo-generated electrons across the interface and providing a redox pathway with low overpotential. So the semiconductor metal heterostructures such as CsPbBr3 bromide gold are useful in photocatalysis and photovoltaics. However, it still remains a major challenge in photocatalysis to design stable and tunable perovskite metal heterostructures. So the obvious question then would be like, why it is so difficult to design a perovskite metal nanoassembly that can be directly employed in a photocatalysis process. So I focus mainly on the design of these metal semiconductor heterostructures and also the interfacial processes happening in them. So the deposition of the metallic gold nanoparticles on the surface of the CsPbBr3 bromide was achieved by the addition of a low concentration of Au3 plus ions. So as you see in the scheme here, the Au3 plus ions, they are reduced by the surface ligands of the CsPbBr3 bromide, which is allylamine and oleic acid, to Au0 and further nucleates to form the gold nanoparticles, which is typically of less than like 2 nanometer in size on the surface of the CsPbBr3 bromide. Since the surface ligands itself reduce the gold, there are no additional reagents are required for the reduction. And also, the hybrid structure allows direct contact between the gold nanoparticles and the CsPbBr3 bromide. So the transmission electron microscopy images analysis here, it confirms the formation of the gold nanoparticles on the surface of the CsPbBr3 bromide. And it also indicates that no noticeable morphological change occurred in the CsPbBr3 bromide upon the deposition of the gold nanoparticle. And as I said, the perovskite, the bright green emission of the CsPbBr3 bromide, it provides a convenient means to probe the excited state interaction with the small gold nanoparticles. So the excited state interactions were tracked using the emission spectra, the photoluminescence decay, and transient absorption spectra, which we will look into. So here, I think you guys can see the spotlight. Yeah. So here, the quenching of emission can be understood from the ability of the gold nanoparticles to serve as electron acceptors. So as I mentioned earlier, these small non-plasmonic metal nanoparticles have been shown to capture electrons and store electrons from the excited state semiconductor nanoparticles. The smaller the size, the greater the number of electrons that can be stored in the metal nanoparticles. So thus, the excited state deactivation can be understood from the emission spectra and also the photoluminescence decay. So the emission spectra showed a maximum around 510 nanometer, which is decreased upon the addition of the Au3 plus ions. So the black trace here, it indicates the emission spectra of the bare CsPbBr3 bromide, which was completely quenched upon the addition of almost around 17.5 micromolar gold ions, which is observed in the red trace here. To support the quenching, photoluminescence decay was also monitored at the emission maximum, which is 5 nanometer. So even without like any fitting parameters, so these decay curves were fitted using a bi-exponential fit, but even without the decay parameters, it is clear that the decay curves, from the decay curves, that the lifetime of the CsPbBr3 bromide nanocrystals, which is shown in the black trace, it decreased to the red one when the gold is added. But again, looking at the numbers, the average lifetime decreased from 6.9 nanoseconds to 1.2 nanoseconds, which is really fast. So the decreased lifetime with increasing the gold concentration, it supports the electron transfer quenching of the CsPbBr3 bromide by the gold nanoparticles. But in order to further assess the ultra-fast kinetics of this electron transfer, we carried out femtosecond transient absorption measurements. So I haven't shown the images here, but the result, the ultra-fast rate constant of the electron transfer between them was found to be around 1.7 times 10 to the power second inverse. So this ultra-fast electron transfer is consistent with the rate constants observed for other semiconductor metal system, which is reported in the literature. So whatever talked till now has been shown in this net reaction, where the perovskite under the radiation, it forms the electron-hole pair, where the electron is transferred to the metal. So we elucidated and quantified the electron transfer processes. But the application of the cesium lead bromide metal in the photocatalysis is yet to be explored fully. So in order to assess the long-term stability, we subjected the cesium lead bromide gold solution to steady state radiation using 1 sun white light, which is 100 milliwatt per centimeter square. So as we continued the photo irradiation, we saw the recovery of quenched emission, which was intriguing. So the two figures here on the top, it shows the emission spectra of the cesium lead bromide gold nanoparticle suspension kept in dark and also under continuous irradiation. So with increasing time, we saw an enhancement in the emission as we continued the light irradiation for almost around 30 minutes. So this figure here, it comprises of both this one. So it shows the photoluminescence recovery following the light irradiation. So more than 95% of the original photoluminescence was restored during this process. We also checked this emission recovery for other cesium lead bromide gold samples where different concentration of gold was added to the cesium lead bromide. So, but we saw a similar recovery of the photoluminescence following steady state elimination. So we had this question, why the emission is recovering back under radiation? So the reason we could think of was that the gold nanoparticles are no longer interacting with the cesium lead bromide. As I mentioned during the synthesis, the gold nanoparticles are deposited on the surface of the cesium lead bromide. But now, if it is not interacting, so what is happening to the heterostructure? So to visualize the morphological changes, we sampled the cesium lead bromide gold suspension at different photo radiation times and carried out the transmission electron microscopy analysis. And the images recorded at 4 different times are shown in the figures. So once they are subjected to the photo irradiation, so this is when they are not subjected to radiation at 0 minutes, but when they are subjected to irradiation, these small gold nanoparticles, they became detached. And these small gold nanoparticles seems to form a network of clusters. With continued irradiation, the gold nanoparticle clusters grow into larger size, which is around 20 to 100 nanometers. So thus the formation of these large gold nanoparticles precludes any direct interaction with the cesium lead bromide, thus restoring its original characteristics. So, but in majority of the examples previously reported, anchoring of metal particles on semiconductor surface, it remains intact even during extended period of photoradiation. So this result here describes how unusual the photo effect of expulsion of the gold nanoparticles from the cesium lead bromide gold heterostructure is. So unlike other semiconductor nanocrystals, the surface of the perovskite nanocrystals is susceptible to environmental changes. It's dynamic in nature. So, and also one other possible explanation for the expulsion of the gold nanoparticles appears to be the charging of the gold nanoparticles during the photoradiation, leading to their expulsion, which is shown in the schematics here. So initially the gold nanoparticles are anchored on the semiconductor, but when we continue the irradiation, the gold nanoparticles will become charged and it will be detached, leading to an aggregation, forming bigger gold nanoparticles. So to conclude, a stable design of the perovskite metal heterostructure still remains a challenge. So the gold nanocrystals formed from the reduction of the oleolamine ligand are loosely bound on the semiconductor surface because the surface is dynamic in nature. And the Au3+ was reduced by the surface ligands of the cesium lead bromide, and the gold nanoparticle was deposited on the surface. And the photoluminescence intensity and lifetime was decreased as electron transfer lead to a non-radiative pathway, and the transfer rate was found to be around 1.7 times 10 to the power 10 second inverse. So these non-plasmonic nanoparticles become charged and get expelled due to steady state radiation. So going forward, we found that the electron transfer is happening. It is up this heterostructure is applicable for photocatalytic applications, but still it is unstable under the radiation. So the use of bifunctional molecule bridge will establish a strong linkage between the semiconductor and metal nanoparticles, which might be stable under radiation as well, which we will look into further. So yeah, I acknowledge Department of Energy and Rad Lab for funding and supporting the project. And thank you, ND Energy, for giving me the opportunity to present my work. So I'd be happy to take any questions.
All right, thank you very much. Are there any questions from the audience? So one question would be, is there a way to make them go back and be bound to the perovskite once they're aggregated?
No, they cannot go back. Because our main aim of this one is the semiconductor. So even though it is used in light harvesting system, the electron hole pair formed, we have to extract the electron to use it as a light harvesting system. So the gold nanoparticle here, when it is only below like 2 or 3 nanometer, then only it will act as an electron acceptor. But now, when it comes out, it also ripens and forms bigger nanoparticles. Now, yeah, it cannot go back.
All right, are there any other questions?
So one quick question, this is Subhash. You mentioned that you cannot really go more than like 2-3 nanometers in size for the particle, is that correct? Yeah. So when you are now looking into using a molecular bridge, what kind of system you are looking at? Are you looking at?
So what I mean by molecular bridge really is here, I'm actually adding Au3+ ions. So the ions itself get reduced to Au0. So the Au0 for the nucleus to form the nanoparticles. But if I'm using a molecular bridge, I will be able to form like gold nanoparticles outside. Like this is kind of like an in situ production of gold nanoparticle. But I can synthesize the gold nanoparticles separately, which has a bifunctional ligand as a capping agent, and I can add it so that it can bind to the cesium and bromide. But yeah, so that's my aim, like whatever I mentioned, by using a bifunctional molecular bridge. So I don't need to add the ions. Instead, I can directly add gold nanoparticles, which is already synthesized. If I can synthesize it by the capping agent, should be like a bifunctional molecular bridge.
Okay. So you develop a process during which this can happen.
My colleagues are actually like, because these perovskites are very unstable in polar environments. I think one of my colleagues will be presenting today regarding that as well. So if it's more stable in polar environments, then whatever I mentioned will be more easier to do.
So so it will be a different way of doing things, right? I mean, it's not an additional step. It's just a different way of.
It's a different way, yeah.
Perfect. Yeah. Okay. Yeah. Thank you.
All right. Thank you, Jishnu.
Yeah.
All right. Our next presenter is Anthony. If you could share your slides.
Right. Everyone can hear me, right?
Yes. Okay. You're all set.
Okay. Thank you. So my name is Anthony Kipkorir, and I work in radiation lab together with Jishnu under supervision of Prashant Kamat. And I'm happy to join you today and contribute to the running theme of this symposium, which has been like the net carbon neutrality, and show you what to do behind the scenes to ensure this happen and even much better end up reducing the carbon footprint. So my work is in photodynamics of cesium-lead bromide CDS heterostructure. And these are basically perovskites that have been capped with CDS, which is another semiconductor, all in the spirit of making sure that it is stable in polar environment. So I'll introduce what perovskites are and why should anyone care about it. So perovskites are basically, you know, building blocks to designing photocatalysts that we can use. And one of the limiting, one thing that limits its application is its degradation when exposed to polar solvent or polar environment. And we found out that by coupling it with an inert semiconductor on the surface, then you are now able to not only make it, polar environment tolerant, but also improve, charge separation, which is a feature necessary for its application. And we thereafter, tested all these excited state interaction using a molecule called ethyl vialogen, just to offer us insights into how it, the new CDS that is cupping the surface is affecting the electron transfer processes. So in the methodology that we adopted is we did like the normal synthesis of the semiconductors, the perovskite semiconductors, and took another route of now putting a CDS, coat over it. This is basically an inert, giving it an inert service that is making it, operational even in a polar environment. And the stability of this was put in, we simulated a polar environment using ethanol solvent, and we monitored the changes in absorption and the PL spectra. And thereafter, when we realized now it's, stable in ethanol, we were able to check its excited properties using ethyl vialogen. And these are just the energetics telling us, where the electrons and the holes are going. So the techniques that we actually put into use here, one is the PL quenching, or the photoluminescence quenching, transient absorption spectroscopy, as well as steady-state photolysis. So right into it, stability in ethanol. So what we did was to subject both the pristine cesium lead bromide and the CDS cupped cesium lead bromide. The blue trace is for the heterostructure, which is cesium lead bromide CDS, and the red trace here is basically the pristine, or rather a synthesized cesium lead bromide. And as you see, when you cup it with CDS, what happens is just an enhanced absorption because of the introduction of this extra exciton peak corresponding to that of CDS, but nothing is happening to the PL spectra. It just remains the same, even the width or the bandwidth just remain the same. So we are not introducing, other features to the perovskite, but just enhancing it workability. And we therefore put it now in 15% ethanol, and to just test whether it's stable or not. And as you can see, the synthesized cesium lead bromide could not stand the polar environment, whereas the CDS cupped one at least tolerated and remained to, around 80% of initial PL was able to actually, remain. So we went ahead to check the excited state properties by now, using the ethyl vialogen, as I mentioned earlier, just to see, is there any interaction? And one of the interesting, features to look at is, can this, molecule quench your emission? Because that will hint that indeed we have an interaction between the two. And indeed we witness even up to less than 20 micromolar is enough to quench the entire emission. And an interesting thing also is, as you see the, the PL, the lifetime is becoming faster and faster as you increase the concentration of the quencher, in this case, ethyl vialogen, signaling that we're having new recombination pathway that is faster than, when you only have the perovskite, or rather this heterostructure. And this we attribute to this electron transfer, which happen in picosecond timescale, and then the contribution now becomes, faster electron transfer, and thereafter, relaxation to the ground state, And that is why you see faster recombination, or rather faster decay, as you increase the quencher concentration. So to see the kind of interaction between the semiconductor, the perovskite, and ethyl halogen, we evaluated it using a double reciprocal plot, because any linear dependence that you obtain from this plot tells you that indeed the kind of interaction you're having is formation of complex at the ground state, where your semiconductor and the molecule that we are using to probe it, in this case the halogen, form a complex in ground state, and you can relate them using the apparent constant. That apparent constant here we're calling K up, and using the relating it now using the double reciprocal analysis, you can get the apparent association constant, which is in order of 4, indicating that indeed we have a strong interaction between these two guys, and therefore you can separate the charges and shuttle it to whichever system you want to reduce or oxidize. And just to give us insight into what is happening, because you cannot resolve using the PL decay, because you're operating in a nanosecond time scale and the resolution goes up to 10 nanometers. But now we need to see things that are happening in picosecond time scales. That's why we are using transient absorption spectroscopy. And again, we see similar trend. Increase in concentration shows that there is faster recovery of the bleach, which indicate that again, this is an introduction of a faster pathway, that in this case we are saying an electron is being transferred to ethyl halogen, and in that case you can now shuttle it to another system. And we calculated the electron transfer rate to be in order of rate constant to be in that order of 9. Finally, just to see visually what is happening, we did steady state photolysis by putting your perovskite together with ethyl halogen and bombarding it with photons all the way from 400 to 900 nanometers, and see what is happening. Because one thing about ethyl halogen is ethyl halogen, what is it in this state of 2+, is colorless. But if you inject electrons to reduce it to ethyl halogen radical, it's blue, and you can now monitor the growth of emission, and it has a characteristic peak at 605 nanometers. And then you can see, as you increase, the time of exposure, you see growth of ethyl halogen radical, indicating that indeed we are injecting electrons into the molecule and reducing it to ethyl halogen radical. And we did a control experiment to say, hey, look, perhaps this could be coming from just ethyl halogen, or this light is shining on ethyl halogen and it's electrochemically converting it to the radical. But we ruled that out. As you can see, the contribution is just near negligible. And the quantum yield of this conversion is 9%, meaning we still have some work to do to ensure that the 91% the underutilized ethyl halogen is brought into the equation. So in conclusion, one is that we are able to stabilize cesium lead bromide by coating it with CDS, and this enabled the studies that we undertook. And again, as I mentioned, faster emission decay indicate that we have a new recombination pathway that is coming up. And evolution of ethyl halogen radical that we monitor in steady state photolysis shows us that indeed we have an electron transfer happening, which is something to smile about as far as application of such material is concerned. And again, use of ethyl halogen provide a nice avenue for us to separate the charges and shuttle it. And why should anyone care about this? With charge separated, you can now use it in light harvesting and other photocatalytic application, which has been pointed out. And all this is done with the aim of again achieving what has been running as carbon neutrality. And I want to thank the Notre Dame Radiation Laboratory, as well as the DOE, who is supporting this work. And also, I want to also acknowledge ND Energy for giving us a platform to showcase our contribution behind the scene, quote unquote. Thank you.
All right, thank you very much, Anthony. Are there questions?
So, Anthony, this is Subhash again. I'm somewhat going out on the limb here because I have not followed your work. But
no problem.
So, when you talk about the CDS coating, again, how big are these particles, and how do you ensure? Do you need to ensure that the coating is uniform, or I'm just sort of asking because I'm trying to understand. It seems to be pretty effective.
Yeah.
So what kind of coverage do you need to get this done?
Okay, so for now I can say you cannot ascertain. I mean, you can measure and see the kind of thickness or the thickness size you have, but for our case, we add a thin coating that you cannot even resolve using the available TEM in our institution. So it doesn't matter the size, because again, increasing the size of the shell can inhibit these electron transfer processes happening. I mean, right. It's a trade-off, yeah. So the thin the shell, the better.
So are you able to, so like, is there a physical characterization you can do by using, say, AFM or a technique, probe technique, which is
just to show that we have a shell, or what are you saying?
Yeah, but also you can potentially do some EV curves, or there are techniques. We also have a mirage where we can actually use a smaller. I don't know what your particles are. What size?
Again? 20 nanometers.
20, yeah. So that's kind of small because in the mirage we are able to produce I think a beam which is around a micron or 2 microns. So that's still a little too big, but you are able to get spectra from that small region. Yeah. So I was just wondering if you have. I mean, I understand the measurements you are doing, and they're pretty elegant. And I'm actually pretty impressed with the ethyl viologen use. Are they almost like a, what should I say, non-contributing?
Because
indicator, but
yeah.
So I was wondering if there are any physical explorations that can be done.
Yeah, I mean, you're right. Ethyl viologen and the sample are actually meeting in different, regimes. So
right.
Yeah.
Very nice work. Yeah. Thank you.
Thank you.
All right. Thank you very much, Anthony.
You're welcome.
Right, and our last poster is from Jeff.
Can everyone hear me? I'm doing the audio dial and might be a little sketchy. Okay, yes. Awesome. I'll go ahead and share the poster. Does it look good?
Yes, we're good.
Wonderful. Okay, so yeah, I'll go ahead and start. So hello everyone. My name is Jeff DuBose. I'm also a graduate student for Prashant Kamat's group. And today, I'll be talking a little bit about this story, a very recent story, very fresh result, looking at energy transfer in our favorite Perovskite nanocrystals that you've been hearing so much about lately, and specifically looking at different types of ways that we can basically transfer energy within these potential light harvesting materials. So with that, I'll go ahead and zoom in a little bit just to make things slightly easier to see. So these perovskite materials, like you've probably heard a couple times now from the other two posters, specifically the cesium lead bromide material, they're very promising candidates for photocatalysis. Again, photocatalysis being the use of light to drive important chemical reactions that can, for example, make sustainable, solar fuels that we can burn later on. So when it comes to photocatalysis, it's oftentimes beneficial to really extend that lifetime of the photogenerated charges that you get from your photocatalyst of interest. And as Anthony was talking about, one way is ethyl biology and other sorts of things like that. But one thing we can do specifically is look at storing energy in what's called a triplet state, which are these long-lived excited states due to different electron spin interactions. And so I'll just go ahead and spin on over to this side of the poster. But this is sort of our prototypical what's called a singlet state, where we essentially have an electron in the ground state, an electron in the excited state because we've had absorption of light. And because these spins are oppositely directed, this is a fairly short-lived state. These triplet states, though, have basically 2 spins up or 2 spins down, and that means that you have a much longer lifetime. So one thing we're trying to do is basically see, hey, can we actually make these triplet states because these will be useful for photocatalysis. So kind of the main thing we want to do is see, one, can we actually do this, and also what is the mechanism of interaction? And so again, the system that we're looking at is the cesium lead bromide nanocrystals. They have excellent light absorption properties, so we should make a lot of these states when we use this as sort of a sensitizer. One nice thing about these perovskite nanomaterials is they're also very chemically tunable, which I'll talk about as like a future direction. And what we're going to look at basically is we're going to excite this with light. We're going to produce excited electrons, and we want to see, does that energy move as a triplet or does it move in form as singlet? And we're going to basically use, in this case, rhodamine B as a dye molecule which can potentially accept both triplets and singlet states. And the reason why we use this rhodamine B dye molecule, one, it's a very well-studied molecule. There's a lot of literature kind of results out there. It supports both the singlet states and the triplet states. And because it has such a well-described behavior, if we are seeing different interesting interactions, like the formation of either one of these states, we'll know what's happening because we know spectroscopically all those different interesting features. Okay, so that's sort of a little bit of the why we're doing this. If we start to look at the data that we get, as you've seen just now in Anthony's poster, one thing we could do is photoluminescence quenching. So essentially, in this case, we're having the nanocrystals. When we shine light onto them, they produce their own light. And as we add more and more of our rhodamine B molecule, we can see what happens to the emitted light from our materials. And so this is a trace here showing that as we go on progressively adding more and more of that rhodamine B dye molecule, we see less and less light being emitted from our cesium lead bromide perovskite nanocrystals. So that's what's happening here, and that shows us that there's deactivation of the excited state of the nanocrystals, some sort of interesting excited state interaction. But down here in the 500 to 700 nanometer range, we also get a bit of a bump, and that's been zoomed in on this part. And this is basically emission coming from the rhodamine B dye molecule because it has its own emissive features. And so one question we have to ask ourselves is, what is the source of this emission? And so one way that we can actually get at that is by taking what's called a photoluminescence excitation spectrum. And so I'll zoom in a little bit more for this one. But essentially what we do is we park our detector out here at 650 nanometers, and we look at all the light that's coming in from the rhodamine B molecule specifically. And what we do is, okay, so we're going to look at the emission from this, and we're going to basically excite at different wavelengths and see at what wavelengths do we get different peaks. So if you follow this red trace here, as we move around from 600 to about 500 nanometers, we see a peak here. So that means that there's something absorbing in this region that's giving rise to emission from the dye molecule. Then we see that peak lowers, and then we get a secondary peak, and then it goes on up and up from there. So that tells us, okay, there's two things that are giving rise to the emission. And so what I've done down here is I've also overlaid the absorption spectrum of the rhodamine and of the nanocrystals. And we can see, so as we excite directly in the rhodamine B region, of course, if we excite rhodamine, we get rhodamine emission. But that absorption decreases down here. But we have a concomitant increase in emission in this region. And what I've also done with the green trace is overlaid the cesium lead bromide absorption spectrum. So this tells us that even though we don't have any absorption from the rhodamine, absorption from the cesium lead bromide nanocrystals is giving rise to rhodamine emission. And so that tells us that there's this definite contribution from the nanocrystals in that emission from the dye, and that's actually suggestive of not triplet energy transfer, but singlet energy transfer, which was a little bit interesting because we weren't exactly expecting that. So this gives us sort of an initial state that we can kind of look at what's happening. If we want to dive into things a little bit deeper, we turn to transient absorption spectroscopy, as again, Anthony had talked about before. And so to give a little bit of background, transient absorption spectroscopy is this sort of fancy laser technique where we come in with two different laser pulses. And essentially what we do is in step one of transient absorption, we take an absorbance spectrum of the ground state. So all of our electrons in our materials are sitting in their normal happy ground state, and we just take a basic absorption spectrum with a laser pulse. And then in step two of transient absorption, what we do is we first come in with a pump pulse, and that excites a bunch of electrons into a higher energy level. And then while everything is still excited, we come in with another probe pulse, and we basically take absorbance in the excited state. And so what we do is we take the difference absorption between those, And that's what you get here in these spectra to the right. So you can see if we look at just the nanocrystals by themselves, you get this nice negative feature here, and that decreases over the course of 1,000 picoseconds. And so that's basically the electrons that have been excited, and as they relax back down, we get a loss of that signal. And I've just zoomed into this region of interest on this right one. So now when we add the rhodamine B dye molecule into the system, again, we see the same kind of feature from the cesium lead bromide nanocrystals, but now we see a little bump down here. And if we zoom into that, now we actually see the transient absorption spectrum coming from the rhodamine B. So now, just like in PL or the photoluminescence spectrum, we have basically two different sets of signals that we can track. So this is the spectra. So these are useful, but what we normally do is we normally look at the kinetics of these signals. So we look at how fast are these signals basically decaying back down to zero. So that's what's going to be shown down here in this panel. So if we first look at these signals coming from the cesium lead bromide nanocrystals, and we look at the kinetics of those, we can see, okay, so this black and this red trace is for the nanocrystals without any methylbiologen, or without any rhodamine B. And as we go on adding more and more of that rhodamine B, we actually see a faster decrease of the cesium lead bromide signal. Again, this indicates that there's deactivation of that cesium lead bromide excited state, basically part of that energy transfer interaction. So that's what's happening with the cesium lead bromide signals. The slightly more interesting thing is what's actually happening with the rhodamine B. So if we look at the rhodamine B spectrum, this is a reference spectrum of the rhodamine B just by itself, and then on the right here, just with the nanocrystals and the rhodamine B. So what we can do is if we look at the kinetics of these two, this is the black trace here, we get basically an instantaneous appearance of the rhodamine B signal, and that starts to decay over the course of 1,000 picoseconds. Now, when we have the rhodamine B and the nanocrystals together, this is that red trace, and I'll try to zoom in a little bit more. Instead of having an instantaneous appearance, we get this very slow and finite rise of the signal, which grows in at about 200 picoseconds, and then it starts to decay after that. And so it may not look like a lot, but this is actually basically the evidence of that energy transfer process. We're getting more and more movement of energy into the rhodamine, and that's causing this very finite and very sort of slow decay. Slow, again, 200 picoseconds is fast for some processes, but in this case, that's a lot slower than that instantaneous appearance. So this tells us, this is basically the evidence of that singlet energy transfer that we saw from the photoluminescence data, but now we can actually see the time scale of how that's growing in. Okay, so I'll zoom out a little bit, and we'll go ahead and conclude and look at future directions. So what we see is this direct evidence of these excited state interactions between our nanocrystals as sort of a sensitizer and this rhodamine B dye molecule. From photoluminescence and also transient absorption, we can see the deactivation of that excited state. Again, from this photoluminescence excitation data here, we can see that not only absorption from the dye, but also absorption from the cesium lead bromide is giving rise to that emission from the rhodamine. And that tells us that although we wanted singlet energy, or we wanted triplet energy transfer, we're actually mostly seeing that singlet energy transfer, which, okay, we'll take it. We'll take what we can get. And then again, from transient absorption, we can see the time scale of that. So as a future direction, we want to basically first confirm that there is no actual triplet formation. There is a possibility of a small percentage of triplet energy transfer happening. So as a future direction, we'll confirm that with longer timescale transient absorption experiments. If there are both of those states being present, we'll go ahead and quantify the ratio of those two, which should be a fairly straightforward process. But the interesting thing that I think for the future direction is actually modifying these nanocrystals to either prefer more singlet energy transfer or more triplet energy transfer. And so as I kind of hinted at the beginning, one nice thing about these nanocrystals is they're very chemically tunable. So we start with the cesium lead bromide nanocrystals, but what we can actually do is we can actually alloy a little bit of iodide into the nanocrystals, and that takes the energy levels of the parent nanocrystal, and that can either make it a smaller energy gap or a larger energy gap if, for example, we alloy a little bit of chloride. And so one thing we want to do is basically look at, okay, can we actually change the energy of the sensitizer of the nanocrystal and see if that weights things more towards singlet energy transfer or more toward triplet energy transfer. And in that way, if we could chemically tune, sort of design our system more toward one, that would be quite interesting. But with that, I'll just go ahead and zoom out and wrap up, and I'll take any questions that anyone has.
All right, thank you very much, Jeff. Are there any questions from the audience?
I'll put this back up.
Yes, thank you, Jeff. Yeah, very interesting talk, I must say. So please correct me if I'm wrong. So you have not explored the triplet state in terms of its long-lived character yet, right? You have not fully explored it yet.
Correct. Yeah, this is like as of the last 2 or 3 weeks kind of data. So this is fresh off the spectrometer. But to answer that question though, so one limitation is that our main transient absorption setup only goes up to 1,000 picoseconds, which is fairly short. If there was triplet energy transfer or triplet formation, we would see it out here at around 650 nanometers. But it's a fairly weak extinction coefficient, so we don't see a lot of signal. And also the nanocrystals themselves, unfortunately, have a lot of induced absorption in that region. So if you have a very small signal, it has to overcome all of this kind of noisiness we have out there. So as one thing we're going to do is look at what's called flash photolysis, which uses a much higher energy laser, or higher intensity, I should say, and then looks on like the microsecond, millisecond kind of time scale. And we're hoping to find triplets there, if there are any. If not, then we'll see from there.
That's very exciting. I would say, I don't know if I should call it discovery or, but it's a very interesting area. So do you think temperature would be in any way a factor in this, or no?
It can, in some cases when you're forming triplets, it can definitely play a role if you get actually reverse movement of the energy, depending on where the triplet and the singlet energy levels lie. There are some temperature dependent movement from a triplet state back to a singlet state if it's a very small energy difference between the singlet and the triplet. In this, for rhodamine, that shouldn't actually be the case, but that is a possibility for other systems where you actually want to design and you want to basically make a triplet that eventually thermally activates back to a singlet and then recombines.
Yeah, you made an excellent point that this is a tunable system, so you still have room to explore. This
is big for us. This is really big. And the other kind of handle that we have to potentially modify things is the size of the nanocrystal. So if we were to make the nanocrystals a lot smaller or make them into like a squished platelet version, then you get a lot of wave function. Basically, the wave function of that material extends past the material a lot more. And then if you have a bound dye molecule, you can get really, really strong coupling. And in some cases, you can see a lot better triplet energy transfer if you go to a smaller nanocrystal. But those are also less stable, so it's a little bit of a trade-off there. So we're gonna stick with the chemical changes for now. But that's an interesting. We have kind of like multiple different kind of knobs to tune.
Yeah, I would say these are also applications in some other areas which potentially we could discuss later. This is not the avenue for that, but yeah, it's pretty interesting find, I would say. Thank you.
Yeah, definitely. Yeah, I know some people look at singlet and triplet formation to basically up convert or down convert light so that you can extend the spectral window of like a solar cell. Yeah. You can either take low energy light and then up it to a higher energy singlet and then inject that into the solar cell and then kind of push the boundaries of solar energy. So that would be an awesome future direction. But we'll see.
Yeah, thank you.
All right. Thank you very much, Jeff. And thank you for all three of our student presenters for giving us insights into their current research.